This tutorial will demonstrate the powerful composite beam design options available within ETABS. This model consists of a 2-bay by 2-bay grid, in this case a subset of a larger building for a floor framing study. All of the framing in this subset model will support gravity loads only. The bays are 36 feet in the X direction and 24 feet in the Y direction. We start by adding columns. We will go down to the base level and fix the columns. Next will be the beams or girders on the grid lines. We select the Gravity Beam Auto Select list and set the moment release to pinned. Again, these members carry only gravity loads. A right-click on a member will bring up the information form. Here, for this girder, the section property is set to W21 by 57, which is the median section from the Gravity Beam Auto Select list. For this model, we do not want any of the perimeter girders designed. We are primarily interested in sizing the interior secondary framing. To change the design procedure, we select the beams and go to the Design Overwrite Frame Design Procedure command. In this case, we could select No Design, Default, Steel Frame Design, or Composite Beam Design. In this case, we choose No Design for the selected beams. Before we draw the secondary beams, we will review the Auto Select list for the composite beams. The beams range in size from a W12 by 14 up to a W16 by 31. Next, we will add in the composite secondary beams. Switch the number of beams to 5 and make sure that they are set parallel to Y. Now we will add the floor deck with the Create Areas at Click command. Reviewing the deck property, we see that the deck has 3.5 inches of concrete over 3-inch deep ribs. A right-click on a secondary beam shows that the section is set to a W14 by 22, which is simply the median size member in the composite beam list, and that this member is to be designed compositely. The program assumes composite design because the member is horizontal, it is pinned at both ends, and it is either an eye or channel shape. All of the composite design controls are available through the Design Composite Beam Design Preferences command. On the first tab, we can set whether the beam is to be shored or unshored. For our model, the beams will not be shored, which means that the steel beam must carry construction loads. The next tab has information on the shear stud, such as the minimum and maximum percentage of composite action and how the studs are laid out. Shear studs allow the transfer of shear force between the concrete deck and the steel beam, and thus provide the composite action. The camber tab specifies the camber details, such as whether camber should be used, which we will, and the minimum camber and the camber increment. The deflection tab allows deflection limits to be set, and here we will set the pre-composite dead load deflection to L/120. The vibration tab allows various vibration criteria to be set, for example walking, and here we will assume a heavily damped floor with a 5% damping ratio. On the Prices tab, we can control whether or not the beam should be optimized based on price. We will set this to No. The last tab allows for adjustment of various fee factors and the reaction factor. This form is also where specific design codes are selected, and for our example, we will use AISC 36010. Next, we will review the load patterns. Two patterns are predefined: a dead with self-weight and a live load. To these two, we will add another case for superimposed dead load. We are now ready to assign loads. We start by assigning the superimposed dead load. Select all 4 deck regions and go to the Assign Shell Loads command and assign a superimposed dead load of 20 pounds per square foot. Now we select the middle beam in the top left bay and assign a point load. This will be a superimposed dead load of 5 kips applied at the mid-span. Lastly, we will assign the live load. Select the deck in the top left bay and assign a live load of 150 pounds per square foot. We will assume that this is for some type of special assembly. Select the 3 remaining deck regions and assign a live load of 50 pounds per square foot. Because of how we have defined the loading, we would expect the secondary beams in these 3 bays to have the same design. However, we will now define a design group that will impose the same member sizes on both the lower and upper left bay beams. Selecting the secondary beams in the left bays, we will assign them to a group named left bays. Going to composite beam design, we will ask that the left bays group be added to our design groups. This will force the program to use the same design for all of the members in the group. We are now ready to run the analysis. With the analysis complete, we will move on to design by clicking the Start Composite Design command. When working with auto-select section lists, the analysis design cycle is iterative, so we need to verify that the analysis and design sections are one and the same. In this case, there are 12 sections that differ. Therefore, we need to run the analysis design cycle once more. This time, the analysis and design sections are the same for all members. Now let's take a look at the section selected by the program. In general, we would expect the secondary beams in these three bays to be the same, namely W12 by 19s. However, the sections selected in the lower left-hand bay are the same size as the top left bay, W14 by 22s. This is because they were all assigned to the same design group, left bays. Thus, the beam size selected based on the loading of the top bay is used in the lower bay as well. The number of studs differs, but the beam size is the same. Let's take a closer look at the composite design. A right-click on a lower left member brings up the interactive composite beam design form, which offers a wealth of information. First off, notice that the beam highlighted in the acceptable designs is the governing design. It shows a W14 by 22 with 14 uniformly distributed shear studs. It has no camber and a ratio of 0.980. The composite action is 46%. Where did the ratio come from? The ratios are all described and listed on the right side of the form. For the design checks, the partial composite bending moment is governing with a ratio of 0.791. This is why this value is highlighted. For constructability and serviceability, the total deflection is governing with a ratio of 0.980. 0.980 is the largest of the ratios and thus is displayed in the acceptable designs list. Note that the shear studs distribution lists the allowable as well. The last analysis box shows that the last analysis and design sections match, as previously determined. All the sections listed below the highlighted section satisfy the design requirements as well. Arbitrarily selecting the W16 by 31 with 12 studs, we see that the percent composite drops to 28% and the governing drops to 0.620, which we can see from the highlighted design check comes from the total deflection. Returning to our original selection, we can see that this member belongs to the left bays group, and that with the Show Group Results checkbox on, our list shows only those sections that satisfy the design criteria of the governing member in the group. The beam and story data shown are for the governing beam in the group. If we uncheck the Show Group Results box, the section highlighted now matches that shown on the plan view, still a W14 by 22, but now with only 8 studs rather than 14. Note that the ratios change to reflect the forces and deflections of this specific beam. Also note that there are now smaller sections in the list that satisfy the design. If we check the Show All Alternates checkbox, the list now includes in red the additional sections from the list that don't satisfy the design. Now let's look at one of the girders. For this member, a W21 by 50 section is selected, and rather than display a uniform distribution of shear studs as shown with the secondary beams, the number of studs required in each segment is shown. Now let's look at the details by right-clicking. Here, this girder is cambered 1.5 inches and has a governing ratio of 0.989. The percent of composite action is 41%, and the governing ratio comes from partial composite bending. We can adjust the percentage of composite action by clicking on the drop-down list, and let's say use 67%. The number of shear studs changes, and we can see how the ratios change. We can also adjust the camber using 1/4-inch increments as set in our preferences. Note how the deflection values change. The preferences for this particular member may be reviewed and modified by going to the Overrides button. For instance, let's say we wish to alter the damping ratio in our vibration criteria. We will change damping to 1%. Note that the girder size has been bumped up to a W27 by 84 from a W21 by 50. And that the governing ratio of 0.965 now comes from the walking acceleration item. The number of acceptable designs is also far fewer. Thus, damping can have a significant impact on member selection when considering vibration effects. Although we defined load patterns, we did not define any design load combinations. The program did this automatically based on the code and the types of load patterns defined. We can review these by clicking on the Combos button. There are 3 categories of combinations: construction, strength, and deflection. Any of these combinations may be viewed by selecting and clicking the Show button. Combinations should be thoroughly checked to ensure that the correct load cases and factors are used. Diagrams of member loading, forces, and deflections may be viewed by clicking on the Diagrams button, and a report for the design may be generated by clicking on the Reports button. This report may be printed or viewed in Word. As a last check, we will verify that all composite beams pass the design checks. This concludes this tutorial.